For our next section, we're going to take a look at spectrum, modulation, and encoding. So to begin with, we're going to take a look at the idea of spread spectrum versus narrowband spectrum. And the idea of the spectrum in general, if you'll remember, in fact, let me just go ahead and pull this up again real quickly. On our electromagnetic spectrum, we had been talking about the fact that our wireless networks were somewhere between the 2 gigahertz and 5 gigahertz, soon to be using the 60 gigahertz range as well. But for now, between the 2 gigahertz range and the 5 gigahertz range. But now we're actually going to take a much more granular look at that spectrum range. So to begin with, what we'll look at, because there are less frequencies involved, so it's easier to draw out linearly on a screen, is the 2.4 gigahertz spectrum. So if we take a look down here, I have an example where I've got the frequency in megahertz. So 2,412 megahertz, and, or I should say from the bottom, 2,412 megahertz, all the way on up to 2,484 megahertz. These comprise the 2.4 gigahertz range of frequencies. And not all frequencies are used in each country. What we do is we actually have, we actually carve up what we call channels. Okay, so if we call channel 1 2,412 or 2412, notice that channel 2 is 2417. So that is exactly 5 megahertz difference from channel 1. So we have to count up 2412, 2413, 14, 15, 16, and 17. There's a 5 megahertz separation between channel 1 and channel 2. Channel 2 and channel 3, 2417 to 2422, again a 5 megahertz. 2422 to 27, 5 megahertz difference, and so on. There's a 5 megahertz difference between each of these. I should say there's a 5 megahertz difference until we get to the difference between channel 13 and channel 14. Okay, and there's a reason for that, but we'll talk about that later. So to begin with, narrowband transmissions send out a signal on just a very narrow portion of the frequency. Okay, it's still probably using 2 or 3 or 5, depending on what the actual technology is, still using multiple megahertz, but or maybe even just a single, very singular frequency, maybe the exact frequency of 2412. Okay, we don't use narrowband transmission in 802.11 specifications. However, for our modern wireless networks. However, it's important to draw the contrast or the difference between using just a single channel versus the idea of spread spectrum. Spread spectrum is just to do, or is to do just that, to spread this, the signal being sent over a wide range of the available wireless frequencies, or as we call them, the spectrum. The width of the spectrum is going to be referred to as the wireless bandwidth. And this is where I stated earlier that I'm going to try, anytime I use the word bandwidth in the context of the CCNA wireless class, and even onto our CCNP wireless classes, I'm going to hopefully most of the time be referring to, I'm going to try to most of the time be referring to frequency bandwidth, not having anything to do with data rate. If I do happen to say bandwidth in conjunction with data rate, I will annotate that. I will specifically say, I'm now talking about data rate, okay? But here we're talking about the width of the frequency band. So if we send a signal out, let's say on 802.11b or G or N, all of which can use the 2.4 gigahertz spectrum, what we're actually doing is, and it actually, when we talk about N, we'll talk about wider bandwidths, but for now, for 802.11b and let's say G, if we send a channel or a signal out on channel 6, 2437, we're actually sending out a 20 megahertz wide channel. So we're actually reaching 5 over here and 5 over there. So that's 10, and 5 over here and 5 over there. We're actually reaching out to 20 megahertz, and we're leaving a little bit on the table for channel 4. Really a little bit on the table between channel 4 and channel 3, and a little bit on the table between channel 8 and channel 9. And there'll be a reason for this, you'll see. But we're using 20 megahertz wide. We're spreading out over multiple channels. I'll just go ahead and say you probably have already heard or read somewhere, even if you're brand new in your CCNA wireless or even wireless in general studies, you've probably heard that with the 2.4 gigahertz, the most popular frequency deployed today, that there are 3, at least in the US, there are 3 non-overlapping channels. So what this means is channel 1, channel 6, and channel 11 in the US. And we're going to talk more about this. But the reason that they're non-overlapping is that they are being spread out. So it's not just using channel 11. Channel 11 is what's called the center channel. Channel 6 is the center channel. So it's spreading out 10 megahertz in either direction. 10 megahertz below the center channel of 2437, 10 megahertz above the center channel of 2437. So really going up to 2436 and down to 2428 rather. And it's a 20 megahertz wide channel. So when we talk about channels, we're talking about that being the center channel. And we're going to talk more about these non-overlapping channels in a little bit. So I'm going to leave that right there for right now. There's something called frequency hopping spread spectrum, and there's something called direct sequence spread spectrum. So FHSS, or frequency hopping spread spectrum, is when we have a narrow band. So maybe we're only using one particular frequency, and it's hopping between frequencies. So it's sending out a signal maybe on channel 2, then all of a sudden on channel 3, then all of a sudden on channel 4, then back to channel 1, then over to channel 2. Whatever it is, the frequency is very narrow. It's using a very narrow singular frequency, and it's hopping between frequencies. That's frequency hopping spread spectrum. We don't use that in modern day 802.11 wireless networks, but it is a type of spread spectrum. And keep in mind, there are a lot of things beyond what we're going to cover in the 802.11 spec, because there's a plethora really of wireless transmission standards out there well beyond the unregulated, unlicensed, meaning they're free for us to use anywhere without having to obtain a license from a federal, governmental type body to be able to transmit on a certain frequency. But these wireless LAN or WAN type networks that we're allowed to set up, there's so many more wireless transmissions beyond that. So there's so many other types of specifications, of encoding, of things than we're going to go over, okay? Frequency hopping was one of the earliest forms of wireless LAN communication. We use something called direct sequence spread spectrum, or DSS. And the idea is that it's a wider pattern. It's a wider bandwidth, 20 megahertz, like I said. Later we'll talk about 40 and even much, much higher. With things such as the 802.11ac, we're going to talk about the ability to have 160 megahertz wide channels for extremely high data rates. But the idea is that if we're sending a signal out over this wider than just a single narrowband channel, 20 megahertz wide series of frequencies, we're sending the signal out kind of all at the same time over these, then we have the ability to send out more data. Okay, theoretically, that's what we can do. So moving on from spread spectrum, we're going to talk about modulation. Now, we're going to bring everything back around and combine it all here in a little bit, but we need to understand first modulation. Modulation is, well, modulating. It's simply changing something. If we are modulating, we're changing a signal in some given form or fashion. We could modulate a signal with amplitude, so we could increase or decrease the power being sent into the signal. Okay, you've probably heard of amplitude modulation, AM radio. AM radio uses power to modulate back and forth the power being sent to modulate the transmission in order to form basically a way of differentiating that signal being sent from other signals being sent. So AM radio modulates the signal with power. FM radio, frequency modulation, modulates the signal based on the frequency. So maybe they change the frequency slightly back and forth. Maybe they change the frequency 2 megahertz in one direction, 2 megahertz in another direction, and they alternate back and forth in various repeated predetermined patterns in order to get that data over to you and then essentially put back together to where your radio can decipher that. But when you switch to AM and FM, really what you're saying is anytime you have an AM FM radio, you have two separate radios that are receiving in very different ways. One is receiving based on knowing how to decode and understand the modulation of the power, the amplitude, and one is able to decode and understand the modulation or the change in frequency. There's also phase modulation. Okay, so I can actually change the timing of the signal peaks. We're going to talk about this quite a lot because one of the modulations we're going to use is called phase shift keying. And it's a very popular one, at least has been in the past. Actually, it's pretty old, but the idea is that we change how the signal is. We start it, and then we stop it, and then we start it again, but instead of starting it right where we left off, we start it at a different place. Okay, we actually drew a little bit of this earlier on, but we will get back on the whiteboard and draw it again so you understand. Okay, so with direct sequence spread spectrum, there's something called a chip sequence. And basically every bit of data is transformed into a sequence that's called a chip, or it's sometimes actually often referred to as a symbol. So if we talk about chips or symbols, we're talking about bits of data, multiple bits of data in a way of basically encoding this. So DSSS sends the data in a string of chips. And Barker 11 was one of the first encoding methods. It's not used today, but the reason that I shouldn't say that. It's not used for high data rates today. It can still be used for low data rates. The reason that we talk about it is we want you to understand the concept of chips or symbols and how they encode or how they represent at a very basic way, how they represent data. So if we take a look here, we've got the idea of, with binary, we have two types, right? There's 10 types of people in the world, those who understand binary and those who don't. Anyway, Think Geek t-shirt. So there's 10 types. There's a 1 and a 0. Really, there's two types, right? Because the 0 is the 1 position and the 1 is the 2 position. Anyhow, so 0, the data is either off, or the 1, the data bit is on. So it's either on or off. Electrically, we can either be on or off. That's it. So a 1 is represented by 01, 001, 000, 111. 0 is the exact binary opposite. So everywhere I had a 0, put a 1, and everywhere I had a 1, put a 0. So if this was 0100, this is 1011. And then I pick back up over here, 1000111, it's going to be 0111100. They're exact binary opposites of each other. These were the encoding methods. And the reason, and so what do we mean by, wait a minute, 1 equals 0, 1, 0, 0. Do I have to use binary to try to add that up and figure out what number that comes to? No. The idea is this is a lack of a pulse of energy. The 1 is a pulse of energy. Lack of a pulse, absence of a pulse, pulse. Absence pulse, absence of the pulse, absence of the pulse, pulse of energy, pulse of energy, pulse of energy. And with this sequence of pulsing out waveforms, pulsing out the energy, we knew if we received that sequence, no pulse, pulse, no pulse, no pulse, pulse, no, 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 pulse, 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 then what we were supposed to think is that should be a binary 1. That encodes or represents a binary 1. If on the other hand, we see pulse, no pulse, 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 no, pulse, 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 no, 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 that represents a 0. Now, the idea was that the thinking behind this was that by expanding the original data of a 1 or a 0, we could sustain certain signal loss. Okay, with wired transmissions, sometimes we have packet loss, but that's really only if we have, buffer overruns or buffer underruns, extremely high amounts of congestion data. That's in wired. In wireless, all bets are off. Okay, in wireless, we have absolutely no guarantee. It's almost like UDP. Now, granted, that's level 4 or layer 4. And we're going to talk about how wireless is a layer 1/layer 2 protocol. Layer 3 and 4 are abstracted. They still retain their benefits. TCP can still be sent over wireless. I'm not saying that. I'm simply drawing the analogy that wireless is more like UDP in the sense that we don't we can't guarantee that everything's going to reach the other end. It's actually also like TCP in the sense that we have to acknowledge or have acknowledged everything that we send out, we need to have an acknowledgement for. So it's kind of like TCP in that way, but it's also kind of like UDP in the sense that we can't guarantee it's going to get to the other end. There is going to be data loss, and maybe let's bring it back down to the layer 1. There is going to be wireless transmission loss. If there wasn't transmission loss, then when I showed you my RSSI earlier, it would be 0. It would be perfect. Okay, instead of being negative 35, I think it would be 0, which is absolutely pristine perfect. But that's only going to be if I have a wired network. In wireless, there is going to be some loss of the transmission signal or reception. So if there's going to be loss, and all we sent was an electrical pulse on to represent bit 1 or bit on, then if we lose certain, portions of that wireless signal, we lose a lot of data. So the idea by expanding it out was, hey, if I happen to lose, let's say I happen to lose this 000, okay, I lose the absence of that electrical energy. And then I hear pulse, 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 no pulse, pulse. Okay? Where does that occur over here? Where do I get pulse, 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 no pulse, pulse? Let's see. Here I've got pulse, pulse, pulse. Then I have no pulse. I do not have a pulse. It never occurs. Because it never occurs, I can lose portions of the wireless signal and still get the rest. It's almost like if you're familiar with hard drives and RAID arrays. It's almost like RAID 5. We're creating parity. We're basically saying I can lose portions of the data, and I can still, from the remaining bits that I get, with some degree of reliability, figure out what was trying to be sent. Was it a 1 or was it a 0? So that's the idea behind encoding and behind expanding out our encoding. Okay, so, and that's the idea behind what we call chips or symbols. A chip or a symbol is basically some form of expanding out the original binary 1 or 0. And there's going to be different methods that we're going to use for this chip or symbol, excuse me. And this chip or symbol is doing what we're calling encoding, and that's what we're about to take a look at, is multiple different forms of encoding by various ways of modulating the signal or changing the signal. So with that being said, let's take a look at some of the earliest ways, which were PSK, phase shift keying. So we've got dB PSK, differential binary phase shift keying, and we've got DQ, not Dairy Queen, but DQ PSK, differential quadrature phase shift keying. First of all, let's just address the idea of phase shift keying. So with phase shift keying, we are shifting the phase. We are altering the signal phase. So the idea is, here we've got our waveform. It's a 2 hertz wave. And here I'm changing it by, I have 1 hertz. I've stopped it. But really, I still have 2 hertz. But instead of starting it right there, I'm starting it back at the top. I still have 2 hertz, but I've changed the phase by 90 degrees. Here, I've changed the phase by 180 degrees. Instead of starting up here at a 90 degree turn in the phase, we talked about phase yesterday, what was in phase, what was out of phase. We even talked briefly about 90, 180, and 270 degrees out of phase. I'm starting it back at the bottom. So I'm literally 180 degrees. If I were to put these two, if I were to put this, this section right here, if I were to cut that and lay it over top of this, it would be 180 degrees out of phase. This is only 90. If I were to cut this section, so these 8 boxes, if I were to cut that and lay it over top of these 8 boxes, I would be 90 degrees out of phase. If I were to cut this bottom piece here that I have my arrow going around, hopefully you can see that well. If I were to cut those 8 boxes out and take this single hertz or single cycle and lay it over top of this waveform here, it would be 270 degrees out of phase. It's basically the same as 90 degrees out of phase, but it's negative 90 degrees out of phase, if you want to call it that. It would be the same thing. So the idea with differential binary, I've got an example here. We're altering the signal binarily, or we're altering it in 2 different directions. So here you see this 1, 2, 3 hertz wave, and then we stop it. So each of these are 1 second. So wherever this, from this black line here to this dotted gray line, that's 1 second. So here's 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. And in these 6 seconds, I have 1, 2, 3, 4, 5, 6 examples of a 3 hertz signal. So that is 3 waveforms, 3 sinusoidal waveforms in each second for a duration of 6 seconds. And so I've got the example of a 1, and then I shift the phase 180 degrees. I'm sorry, no, I don't shift it. I start it. Actually, this is shifting at 180 degrees. And so the way that this worked actually is, if we shift it 180 degrees, what this means is we are changing, we are sending, I believe, a 1. And if we don't shift it, if we continue on, we're sending a 0. At any rate, we're altering the signal by 180 degree phase shifts. With differential quadrature, that's where we get into these 4, where we actually use a quad type system. If we look at an azimuth chart where we've got 0 to 360 degrees, we can cut it up either into, we can cut it up by, let me just draw it actually. Make sure that there's no miscommunication. If I have an azimuth chart, I've got 0 degrees right here, 90 degrees, 180 degrees, 270 degrees. And so if I take and I cut this in half, I've got a binary or a binaural, way of shifting that phase. So I'm shifting it by 180 degrees either way. If I have quadrature, differential quadrature, I'm taking and I'm cutting this up instead of binaurally, I'm cutting it up into quads. So I've got my 0 to 90 degree change in phase. I've got my 90 to 180 degree change in phase, my 180 to 270 degree change in phase, and then back to 0 or 360, whatever you want to call it. Okay, so that's the difference, is I'm either cutting that phase up by 2, differential binary, or I'm cutting it up by 4, differential quadrature. You're going to want to remember quadrature because we're going to be using quads quite a lot, cutting things up into 4 quadrants. Okay, with differential binary, this actually allowed for speeds up to 1 megabit per second. With differential quadrature phase shift keying, we were able to achieve speeds of up to 2 megabits per second. So keep in mind the difference between the quadrature, the quads that we're using, and what it is we're doing. In this case, shifting the phase. Shifting the phase, phase shift keying. Okay, moving on, we had something later called CCK, or complementary code keying. With CCK, basically each symbol or each chip of 6 bits was represented with a code word. Coding of 4 bits per symbol gave us 5.5 megabits per second. Coding with 8 bits per symbol gave us speeds up to 11 megabits per second. Just taking a look at what we've looked at so far, we have various modulation and various encoding. And whenever you take a look at a new specification, or even just go back and look at all the existing specifications, you're going to see that for any given specification, there were changes in speeds, and that was due to either changing the modulation or encoding, or potentially both. So for instance, 802.11, if you're not familiar with that, 802.11 was out before 802.11a and b. Actually, B and A came around right about the same time. And I don't know if you remember anything about that, but I remember deploying 802.11, 1 and 2 megabit per second wireless access points. And let me just tell you, while the access points weren't that difficult to deploy, the client getting drivers for Windows 95 in a 802.11 type, environment were not always that seamless to install like wireless works today. At any rate, those use the Barker chipping, Barker 11, and the 1 megabit used the binary phase shift keying. The 802.11 used the quadrature phase shift keying, or differential quadrature. We called it DQ PSK. Same thing. Okay, with 802.11b, if we used CCK 16 codes and quadrature or differential quadrature phase shift keying, we achieved speeds of 5.5 megabits per second on a 22 megahertz wide channel. We talked earlier about 20 megahertz wide channels, and that's what we use today is 20 megahertz or 40 megahertz wide channels. But the older standards use 22 megahertz wide channels. 802.11b with CCK 128 coding using DQPSK achieved speeds of 11 megabits per second. Then there is a completely different way of dealing with modulation. And we have something called OFDM, or orthogonal frequency division multiplexing. So this was an alternate to using DSSS. So instead of direct sequence spread spectrum, we basically did frequency division multiplexing. You may be familiar with time division multiplexing, TDM, where we cut up, and this is very familiar if you're, or should should say this is very familiar territory if you're used to voice networks in any way, where such things like a PRI, an ISDN PRI, we actually use time, and we cut up time slices, and we stick voice or data into those time slices, and then on the other side, we reassemble those into the proper sequence that we want. With frequency division multiplexing, instead of TDM, FDM, with frequency division multiplexing, instead of cutting up time slices, we're cutting up different frequencies. And so instead of sending one wide combination channel, frequencies are broken up into sub-channels, and we actually call these sub-carriers. Whenever you read any documentation on OFDM, you'll read about the various sub-carriers. So if we were using, let's say, a 20 megahertz wide spectrum, DSSS would directly use the entire 20 or 22, whatever it had to, whatever the case may have been, would use the entire spread spectrum to send data all out at once. With OFDM, frequency division multiplex, in fact, you could, OFDM can be a lot to remember at first, not just the acronym, but the orthogonal portion. But you could remember frequency division multiplexing to begin with. With FDM, or frequency division multiplexing, we're cutting up sub-channels or sub-frequencies, sub-carriers, and each sub-carrier is going to be 312.5 kilohertz apart from one another, okay? Or 3,125 hertz apart from one another. Data is sent then simultaneously over these sub-channels or sub-carriers in parallel to one another. Now, we actually have data protection mechanisms. So in order to ward off, would-be frequency encroaching, people that are using the same frequency or, actually worse, adjacent frequencies that happen to partially overlap, something like that, we actually use some of the subcarriers to protect or guard against these kinds of interference issues. Okay, we use them to control as well, with some control data, control the signal as a whole. Okay, so it's almost picture the 20 megahertz or possibly 40 megahertz wide channel as a bunch of tiny little channels. In fact, let me just draw this. This is one way to picture it. With, let's say we had our channel 1, channel 2, channel 3, channel 4, channel 5, 6, 7, 8, 9, 10, and 11. I'll stop there. That's what the US uses. Europe uses up to 13, and Japan uses up to 14. But let's just stop here for right now. With direct sequence spread spectrum, we were, using basically, with 6 being our center channel, we were kind of using this whole thing as one big solid pipe. And we were sending all of our data through that wide bandwidth pipe. Okay? If we were to take a look again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we were to take a look at OFDM and frequency division multiplexing, we're still using the 20, or it could be 40 megahertz wide channel, but instead of sending data in bulk over that channel, you might actually look at it like, here is pipe, I don't know if I can draw this fine, I'll attempt to. Here's pipe number 1. Here's pipe number 2. Here's pipe number 3. That kind of has a wide bottom there. Pipe number 4. So here's our data, or these are the sub-carriers. These are the sub-frequencies. And then on top of those, we have our protection sub-carriers. So on the outsides, we've got our control. So maybe I have one for control here, and a few for protection on the outside. Guard channels, if they were. And there's a lot more channels, sub-channels or sub-carriers than this. I'm just trying to illustrate a point. So in other words, if this was my, let's just look at it from a side view. If this was my 20 megahertz wide channel, then I would have all of these sub-channels here in the middle, or sub-carriers, sending data in parallel, which means that I can get the data out the door quicker because I'm spending less time. Well, it's not serialization, but similar to that. Sending less time transmitting. And then I've got all these guard frequencies, guard subcarriers. And I've got some control subcarriers as well. So they're guarding against interference and they're controlling the overall signal. Okay, so we got the blue that are kind of controlling the green and the red that are kind of guarding against outside interference or intruders. So that's the idea. Hopefully that helps to make a little bit more sense because OFDM can be a bit of a concept, bit of a difficult concept to grasp at first. That's the idea of the orthogonal frequency division multiplexing, or frequency division multiplexing in general. And of the 52 OFDM subcarriers, 48 are used for data, and 4 are the pilot subcarriers used for the control and the guard. Okay, this is used in 802.11a, as well as G, N, and the AC, the 802.11ac, the 1 gigabit per second standard that's set to be ratified probably in 2013. Next, we want to take a look at something called quadrature amplitude modulation. So amplitude modulation, we're changing what? We're changing the power. Okay, we're changing the overall power in a given signal. But with quadrature, we're cutting up phase shifts like quadrature phase shift keying, but we're combining that with amplitude modulation or changing the power. So we're trying, or we, not we, but the brilliant people that came up with this idea, we're trying to get the best of both worlds. The idea is that we're trying to do more, better, faster, right? Better in the sense that it's a more high quality signal, but we're trying to get stuff more data into the same time frame. Everything's about time. When we talk about bandwidth, let me back up. When we talk about data rates, we're talking about how much data can I get onto a wire, or in this case, out onto a wireless transmission in a given period of time. Now, given the bandwidth, back to radio frequency bandwidth, given the width of the frequency band that I have, what different types of modulation or encoding can I use in order to stuff more data into that almost imaginary, certainly invisible pipe, wireless pipe, in the same amount of time? So quadrature amplitude modulation was trying to use the best of phase shift keying. We're changing the phase in a quadrature fashion, but we're also combining it with amplitude modulation. And QAM is what's used in wireless transmissions today for modern networks. Okay, we have 16 QAM, which is 4 to the second. Okay, so 4 times 4. This is used in AG and 11, 802.11 AG and 11, which is what I actually have pictured here. We can see let's say I've got 25% amplitude. Okay, so I'm within the inner circle here. I only have a certain amount of power being applied. Actually, right now it's on the 50% is where this line is, but here's 25% of power being applied in a quadrature fashion. You can see my quad here. So if I have the phase at, and their phase points are going to be different, how many phase points actually determines 16, 64, 256. So really I have a certain power and a certain phase determines, let's say, 0000. If I have increased power, so maybe I have, this is 25%, 50%. If I have 75%, and I'm in this particular quadrant, which would, based on from the center, probably be about, let's see, if that's 0, then that's probably about, I don't know, 10 or 15 degrees. So if I have 75% amplitude or power, and I have about 15 degrees in my azimuth or my quad, I'm representing the binary figure of 0010, or at least that symbol. So the further out I get, this is an example of 16 QAM. Okay, I have 16 different codes or 16 different symbols, 16 different chips that can be sent in this quadrature given different amplitudes. And as I go out from the center, those are my amplitudes: 25% power, 55% amplification, 75% amplification, and finally 100% amplification. Okay, so that's my 16 QAM. With 16 QAM, I can achieve speeds of up to 36 megabits per second. This was used in 802.11a and G. I actually said N. N doesn't use 16. With 64 QAM, I can get speeds of up to 48. There's actually, before 256, there's actually 128 QAM. I can get speeds of up to 54 megabits. So 802.11g and A both used up to 128 QAM. So that is to say I have 4 quads, 25, 50, 75, and 100% power. And if I were to add all of these quads together, I would have 128 bits, okay, or 128 different, I shouldn't say bits, 128 different symbols or chips, which represent a bit. Okay, I know it can be confusing if you're new to wireless, but this is something you need to understand. Here's a summary of orthogonal frequency division multiplexing based on various modulation. So we already talked about the binary phase shift keying, the quadrature phase shift keying, but now we're talking about that in conjunction with OFDM. We have 16 QAM. And by the way, those subcarriers are sometimes referred to as tones. Those symbols or chips are referred to as tones. So we've got data that we can stuff per tone. And basically 1125 kilobit per second times 128 of those gives us the 54 megabits per second. We use 20 megahertz channel widths or bandwidth of the actual wireless frequencies. This was used in G and A. Now, obviously 54 megabits per second wasn't fast enough for many people. Certainly not around 2007, 2008, 2009, when they began working on and finally ratified 802.11n. So now we have to come up with other ways. Not only we can have higher degrees of QAM, such as 256 QAM is actually used in 802.11ac for 1 gigabit transmission, but we can only do so much with the modulation. Now, I'm sure that newer, better ways will be found. A decade from now, I'll look back and say, 256 QAM, I can't believe we were ever using such ancient technology. But the point is that we constantly push the limits, right? And then we say, well, for right now, we've kind of reached a wall. We know that we have to go beyond that wall and reach higher limits. But until we can go beyond, until we can come up with a way, speculate, theorize, and finally test and prove a way to go beyond those forms of modulation that we have right now, we need to maybe explore other avenues of changing the signal or multiplying the signal, or maybe even having multiple, like I said, having multiple signals. So 802.11n introduced something called MIMO, multiple input, multiple output. The idea was, hey, listen, if I can get at least 54 megabits, maybe even higher, What if I had multiple antennas transmitting, and what if the client could receive multiple signals, not multiple copies of the same signal like we were talking about earlier with diversity, okay? Diversity was two antennas, and we're sending out the same signal twice, and the client basically chose the better of the two. Now we're saying, instead of that, let's send out multiple signals, different signals, and depending on the client, how many antennas they have to be able to receive, then they can receive higher data rates because they can receive possibly multiple, not multiple copies, but multiple different signals, and then sequence those back together. It's almost like fragmenting IP packets, but in this case, we're fragmenting wireless signals, sending them out over. It's almost like having different lines, different transmission lines. So instead of, one transmission line, we now have two, or in this case, three. Now, it depends on how many antennas the transmitter is able to support. The standard supports up to, really N supports up to 4 spatial streams, 4 antennas. Cisco typically has 3 antennas on most of their APs. And in fact, I would say many vendors have about 3 antennas. It also depends on how many antennas the client has. And this really just depends on your laptop, depends on your wireless card. If you happen to have an external wireless card, does it have multiple antennas? Sometimes you can get an external, let's say like a USB connected wireless card, and you might want to, if you want to have really high data rates because it has multiple antennas, but maybe your laptop does not. It's not necessarily convenient to carry it around, but just depends on what your application is. Maybe if it's like a laptop mounted to a mobile tray in a healthcare or hospital environment, and I need to have extremely high data rates to show real-time MRI images for something, maybe I either have a laptop that has a manufacturer wireless card that already has those 3 antennas, or maybe I have an external wireless card because it has 3 antennas and I can receive 3 separate streams at the same time and therefore triple my data rate. Okay, so it just depends on how many. There can be different combinations. So the transmitter could have 3 antennas and the receiver could have 1 antenna. In that case, when the receiver talks to the transmitter, when the client talks to the access point or AP, it's going to let them know, hey, I only have 1 antenna. And so when the AP is directing transmissions to that particular client, it will use its antennas in a different fashion. Okay. That way, maybe it can use them in diversity fashion. So there's a lot of different techniques that are involved in order to get the best possible signal over to the client. And it depends on, like I said, how many antennas each have. So we have these multiple spatially multiplex streams. When I say multiplex, like I said, we're cutting them up. We're sending them out over multiple wireless paths. And then when they get back to the other side, they are demuxed or demultiplied. They are put back together. Beamforming is a technology that we can use the signal from each antenna sent with different phase weighting so that the receiving antenna or antennas, receiving antenna gets the maximum possible signal strength. So this is where I was saying, instead of going back to just the basic way of diversity where we send out multiple copies of a signal, 802.11n, especially when a client only has 1 antenna to receive on, the AP, assuming that it supports this, can actually form its beams 3 separate ways, knowing that multipath is a bad thing, or at least formerly was a bad thing, knowing that my signal is going to reflect off or scatter. And how does the AP know? Well, it does it by sending and receiving packets, or I'm sending and receiving frames. And as it has sent and received a few frames to and then from the client, it begins to build a picture, a virtual picture of, it certainly begins to build RSSI strength values, and an idea of how the client is receiving these particular streams from, and it can do those independently from each of its antennas. So then it says, hey, the client only has one antenna. He told me that. I received different RSSI values from the three different reception of the wireless, transmissions that I got from that client in response to, something that I sent out. And now I'm going to use multipath to my advantage. I'm basically going to say, hey, I've got three different RSSI values. I'm going to form this beam and send it out in these multiple different directions so that I can make the most out of the client's reception. Now, this is an ongoing algorithm that's run constantly in the AP. And the reason for that is the wireless client moves. And when the wireless client moves, when I have my smartphone and I'm walking around, when I have my iPad or Android tablet and I'm walking around, when I have my laptop and I move from a conference room back to my desk, my path changes. And if I'm using that, let's say my smartphone, while I'm walking around, I want that beam to constantly change and form as best it can to my needs. And that's the job of the AP, is to constantly run that algorithm and try to form the beam each and every individual time as best it can. It's an intensive process, but most modern APs can handle that. Then we also have something called MRC, or maximal ratio combining. This is when the receiving client has multiple antennas, and this is used to optimally combine the multiple signals at the receiving antenna. Okay, so beam forming is typically used when the client has one antenna. Maximal ratio combining, or as we'll refer to it from now on, MRC, is typically when the client has multiple antennas to receive multiple signals and then demux those multiply spatial multiplex streams. It can be a mouthful to talk about 802.11n. Okay, each stream, like I said, essentially sends the same amount of base data. 2 streams could effectively double the rate. 4 streams can effectively quadruple it. 802.11ac, what's about to be ratified, and we've actually already seen the first AP show up on the market. Netgear had the first AP. I haven't actually found a price for it, at least not today when I'm doing the recording. I don't think it's been announced, but the actual AP has been announced. And I don't know if this AP has 8 antennas or not, but we can actually have up to 8 spatial streams with 802.11ac. So now let's get back to channels and let's look at channel separation. So whenever we consider channel width, whether we're talking about 22 megahertz in the old spectrum, in the old standards, 802.11b and 802.11 plane, whether we're talking about 20 megahertz spectrum, 20 megahertz bandwidth in 802.11a, g, and n, although 802.11n can use up to 40 megahertz wide channels, and those would typically be done in the 5 gigahertz range because of what we're about to see here with only 3 non-overlapping channels in the 2.4 gigahertz range. And then with 802.11ac, we can use up to 160 megahertz wide channels. Wow. So we talk about 8 antennas, 160 megahertz wide channels, and 256 QAM, or quadrature amplitude modulation. And then you can begin to see how we're pushing. So we're using multiple different things. 8 times the width of an 802.11g channel, really 8 times the width of a standard 802.11n channel. Most don't use 40 megahertz, most use 20. We're also having so much more QAM symbols able to be stuffed into that area. We're effectively doubling the maximum of what 802.11n uses 128 QAM. So with 802.11ac, we're able to double that with 256. So that's double the data rate right there. Then we're 8 timesing, or at least 4 timesing, the maximum 802.11n channel width. And then we also have at least 4 more antennas than 802.11n can support. So we're sending 4 times the amount of data with 4 antennas, twice the amount of data. So that's, 4 times 2, we're at 8 times. And then what was the other thing that we just talked about? Twice. Anyhow, all of these things add together to come up with an extremely high theoretical data rate. Now, we never actually get the data rate that we're promised because of environmental factors, okay? Because no wireless signal is perfect. But we do have this theoretical maximum data rate, and we do achieve speeds that are fairly good. It's actually 802.11ac has there's another body that's probably going to be approved before or ratified before 802.11ac will, strangely enough. I think 802.11ac will be used more for corporate enterprise environments, which is about 1 gigabit per second. And then there's something called Giga Wi-Fi. Giga Wi-Fi is promising speeds of up to 7 gigabits per second, but this is more of actually a consumer-based standard. And I don't think it has quite as much error checking, but the idea of pushing this massive amount of data at home is so that we can have completely wireless, high definition, 1080p, and even maybe beyond 1080p, maybe Ultra HD signals being pushed to and from our TV, Blu-ray DVD player, satellite or cable set-top box, etc. So we don't have to have wires. The only wires we'll need will be the power, the AC power. At any rate, let's look at channel separation. So when we consider the width of our channel, it's important not to allow overlapping of channels. Okay? When we talk about overlapping of channels, when we talk later on today about media access and management frames, and how every frame that's sent has to be acknowledged, or at least has to be listened to at the very minimal if it's on my same channel, okay? Or if it's on my same bandwidth, I have to at least listen to it. And when we talk about collisions and something called CSMCA, in wired 802.3 Ethernet networks, we have CSMCD, carrier sense multiple access, or CSMA CD, carrier sense multiple access with collision detection. We can't really detect collisions in wireless. We simply have to listen and see if anyone else is sending. And because we have to listen, if anyone is sending on a frequency that we are transmitting on, even on these peripheral frequencies out here at the edge, okay, not just in this center channel 6, but on any of the peripheral frequencies, we have to stop transmitting or not transmit to begin with, and we have to listen, and we have to wait till it's quiet. Now, that might sound like almost impossible. In fact, we just talked earlier about noise. How can we be hearing noise if we are completely quiet? Or, I mean, how can we actually really have a signal at all if we're always quiet listening to the rest of the noise? Isn't somebody already or always already talking? Yes, kind of. But remember, just as in wired networks, wireless network transmission is done extremely fast. We're talking about microsecond transmissions and millisecond transmissions. So we have to stop and we have to listen, and then we have to wait and we have to send, and we'll talk about how that entire process works in an upcoming module. But first, the main thing is that if anyone's transmitting on our frequency, we have to stop and listen. So it's very important not to have anyone transmitting on the same frequency as us, or at least to minimize that. In a enterprise environment, let's say I'm in a building that I share the building space with other people. I'm probably not going to be able to eliminate that altogether because I have other people in other offices and I can't go regulate them like a government. I can't tell them what they have to do with their wireless APs. We both rent or lease space from the same building. Now, if I own the building and I'm myself or contracting you to come consult, do a wireless site survey, and set up a a wireless network where I will not have any overlap, that I can control. So if I can control the whole building, I can certainly control the non-overlapping of channels. And it's very important because, like I said, we have this collision avoidance. We have to listen to see if anyone's transmitting. So if I have two people, two wireless cells that are overlapping on the same channel, then we're going to have a lot of collisions, or at the very least, a lesser data rate because I can't send as often in time. So we have, in the US, at least, we have these three non-overlapping channels. Now this shows 22 megahertz. This was for the older standard 802.11 and B. But for 802.11n, you know, what we're doing today in today's networks, or even 802.11g, at the least, we have 20 megahertz wide channels. So there's actually a 25 megahertz difference between channel 1 and 6. So if I take if I just take 437 and subtract 412, I get 25. If I'm using 20 megahertz wide channels, then that means, so just imagine that was a 2-0 instead, then I have a 5 megahertz buffer or a 5 megahertz separation in between those channels. Okay? So the US has 3 non-overlapping channels. We only use up to channel 11. Remember that channel 1 is not the bottom of the frequencies I'm transmitting at. It's just the bottom of the center channel. I'm actually using 10 megahertz below 2412. So I'm actually using down to 2402 and then up to 2422. So I'm using a 20 megahertz wide channel. Likewise, channel 11 isn't where the frequency range stops. It's not where the electromagnetic spectrum stops. I'm actually using 2452, 2462 is the center, up to 2472. So I'm actually using into channel 13. It's just that we don't use channel 12 or 13 in the US for a center channel. In Europe, the specification calls for them to be able to use up to channel 13. In Japan, they can use up to channel 14, and it's spaced farther apart because it's not 5 megahertz apart from the other channels, just like, you know, each of those are from each other. Okay, 2472 minus 2467 is 5, whereas 2484 minus 2472 is 12, so it's actually 12 megahertz beyond. Okay, why it's called channel 14 when it's 12 megahertz beyond and the rest are 5 megahertz separated. I don't know that I've actually ever been that curious to read why, but it is kind of curious, I suppose. Okay, so channels 1, 6, and 11, we can see here, if I have 20 megahertz wide channels and I'm at 2417, that stretches all the way down to here. That's what these dotted lines are. Channel 3 stretches into here. If I have channel 1, the solid line, I am not overlapping with channel 6. In fact, I have a 5 megahertz buffer or separation. Channel 6 has a 5 megahertz buffer or separation from channel 11 being the center channel. So that's what we mean by 3 non-overlapping channels. By the way, let's just say you're in the US. If you're outside, you can, you can change the channels how you like. It's just important that you consider the channel bandwidth and that you don't overlap. And data is less sensitive to overlap than voice and video. Voice and video being much more time delay sensitive, much more sensitive to packet loss, as well as jitter, the difference in delay from one packet to the next. Those absolutely cannot bear channel overlap. I'm not saying data should have channel overlap, but it's a little bit more benign or a little bit more accepting, a little bit more forgiving is a better way of putting it, than channel overlap is to voice or video. That being said, consider one of the worst scenarios, which is not that if I actually have 2 different people transmitting on channel 6, but they're actually two separate, let's say SSIDs, two separate wireless LANs, as we'll equate an SSID to later. That's bad, but what's worse, so that's called co-channel interference. They're on the same channel and they're interfering with one another. What's worse is someone that was on, let's say, channel 3, because they're not only overlapping with channel 6, but they're also overlapping with channel 1. And not only are they doing that, but they're not sending on my direct channel. They're not sending on my center channel, my control channel. And because of that, I'm not necessarily hearing them, but I'm kind of getting bumped around by this overlap right here, the overlap from channel 3. It's bumping the peripheral bandwidth frequencies that I'm using for my channel 6, and it's causing major collisions. So we're going to talk about two things more as we go on. In fact, we have this right now, and that is co-channel interference or adjacent interference. So co-channel interference, when another SSID shares the same center channel, they can cope with this because they hear each other and they see based on that center channel when someone is transmitting, and then they wait to send, something we'll talk about called CSMA CA with back-off timers. It's going to slow each cell down. But adjacent interference is much, much worse, should be avoided at all costs, because devices transmitting on different, however overlapping channels, they can't really hear each other. They'll simply create high noise, but worse, they'll create many, many collisions and reduce data rates significantly. So if I have a device on channel 3, like I began to mention earlier, okay, channel 6 is the channel my SSID called sales is going to be on, let's just say. All right, no problem. I can hear anyone else that's transmitting on the center channel of 6. Someone that's transmitting on 3, I don't hear them. I don't see them transmitting on my same center channel, but I just keep getting bumped. I keep getting collisions by the fact that they're overlapping with my peripheral channels. This is going to cause significant reduction in data rates, not to mention that they're also affecting anyone in channel 1 in the same fashion. So adjacent channel interference, somebody that thinks, oh, you know what? I see somebody, let's say this is actually a common thing that I see in home environments, much more than in enterprise environments. Or in an enterprise environment, someone that brings in their own rogue AP, not approved by the company, and they just set it up. And this is one of the reasons that rogue APs can be such a problem in an enterprise environment, that not all IT professionals realize how much of a problem it can be. But, you know, maybe someone at home or somewhere else, they say, oh, I know enough about wireless to know that there's 3 non-overlapping channels, 1, 6, and 11, and they're all 3 being used. So what I'm going to do is I'm going to stick mine right in the middle of 1 and 6. I'm going to use 3 because nobody's using that, and it's not the same as channel 1 or 6, so it's going to work just fine. It's actually going to cause more problems for them and for the enterprise or other people in the homes. It's one of the reasons I prefer, at least in a home environment, sometimes in a corporate environment, just depends on the situation, on the specification of the client, but I prefer to use the 5 gigahertz band of frequencies because there's rarely as many, if any, people transmitting in that frequency range. Finally, I actually want to say one last thing about encoding the different data rates. So talking about data rates in conjunction with encoding mechanisms and modulation types. And that's something called dynamic rate shifting, or DRS. Basically, as I move farther away from the access point, I have less of a signal strength. And I also, more importantly, I have less of a signal strength. I also have a lower signal to noise ratio is what I was going to say. But because I have less of a signal strength, I can't necessarily get the benefit of all the faster ways of modulating and encoding. So let's go back to some of these. Let's say I'm looking at 802.11g. And as I move away, so let's say this is the center of the access point here, down here at the bottom, and I have the fastest possible speed of 54 megabits per second. As I move away from the center of that client, I can't necessarily hear as much data in the same amount of time. Okay, I can't necessarily do the same or understand the same modulation types or same encoding mechanisms. Because of that, the industry supports something and came up with something early on called dynamic rate shifting. That is to say, as I get further out and can only understand maybe quadrature phase shift keying versus quadrature amplitude modulation times 64 or with 128 symbols, as I go out, I can actually shift my data rate, dynamic rate shifting. I can shift it down to accommodate for the lesser modulation types that I can support at a lesser RSSI. So it's important to understand that as I have a better receive signal strength indicator and a better signal to noise ratio, yes, so less noise, I can support higher forms, faster forms of modulation and encoding techniques, and therefore I get a higher data rate. Now we're going to take a look at later on when we actually look at the interface. And by the way, it's important to get a lot of this theory under our belts and in our brains and fully absorbed before we go take a look at the actual interface. But don't be fooled. We're going to spend a lot of time in the access point and probably more in the wireless LAN controller and WCS, or wireless control system from Cisco. And in the wireless LAN controller, what we're going to see is that we can tell the APs to turn on or off certain data rates. So we could say turn on 54, on 48, turn on 36, but turn off the data rate of 24. Don't support it. Now, what happens if a client gets out to that range and can't support it, can't see it? Are they going to try to transmit using that modulation? No, because when they first boot up, or when the client first begins talking, sends probes or association requests to the access point, inside those management frames, things that we're about to talk about, haven't got to yet, so you don't have to worry, they're going to say, what rates do you support? What data rates do you support, Mr. Access Point? And it's going to say, oh, I support 54, 48, 36. I don't support 24, so it just won't say it. I also support, and we'll see this, by the way, in the Wireshark packet capture. I support data rate of 18. I don't support 12. I do support 9. I don't support 6. So 9 is the minimum that you can transmit at. Okay, you have to use binary phase shift keying. All that's in the standard. The AP doesn't tell the client you have to use this kind of modulation. That's part of the standard. The client already knows that. The AP already knows that. It just knows 9 megabits, so it knows, hey, if I get beyond the ability to do quadrature phase shift keying, I have to dynamically rate shift down to binary phase shift keying and send it 9 megabit. If I get out beyond that and I can't do that, I can only send lower tones or something called OFDM, then basically I'm out of luck. I can't communicate with this AP anymore because he told me that he did not support, or he had turned off, the data rate of 6 megabits per second. What do I do then? Hopefully there's an adjacent AP on a different non-overlapping channel that has the same SSID, and I can begin to roam over to that other AP. Still keep sending data, but hopefully beyond, right about this area right here, I can see both the AP I've been talking to and another AP on a different channel. And the wireless, clients, they can be talking to 2 different APs at the same time, even though they're only sending data to one. They're sending management frames to the other, to both, but they're only sending their actual data frames to one. And then I can dynamically roam very quickly, 10, 20 milliseconds, depends on what we're doing. But I can do something called fast roaming, and I can switch over to the AP, and all of a sudden I'm on the other AP at 9 megabit, and then as I get closer, I can dynamically rate shift up. So I've walked away from the center of one AP, I'm now walking to another AP, and I can DRS, or dynamically rate shift up, to the center 54, and then I begin data rate shifting down. This is assuming that I am actually, continually walking to and from let's say I have a smartphone or something, and I'm walking out of my office to go to lunch, which we're about to do, and I want to keep getting data so I can roam from one to another. But that's the idea of data rate shifting. I can shift up in rates as I get closer to the center of the AP. I can shift down as I get further away, and then ultimately we will roam.